YouTube video. I'm your host, Pavel Savianko, and today I would like to speak a little bit about inclusive and exclusive values in the Cube library. If you have seen another videos on this channel where I present different features of CubeGUI, for example, you have seen definitely 3 trees, and one can expand, collapse of these trees, and there are data assigned to every element of these trees, and one speaks about inclusive and exclusive values in these trees, and normally one understands what's going on. Here I would like to speak about technical part, how Cube library treats this data, and actually make accent on the fact that the Cube library has more general view for inclusive and exclusive values than one might expect, because display of data, for example, for metric time and its calculation, its relationship, it is very intuitive but also a little bit naive understanding of inclusive and exclusive values. Cube library does it in a more general way, and that is where I put accent on this video, because the typical interpretation of inclusive and exclusive values is presented on every webinar, on every tutorial about performance analysis, and there is one doesn't need to watch this video. But if one wants to understand a little bit internals of Cube library, especially if one develops tools, then I hope it will be useful. Before I will do basically coming from the partial case from this simple definition of inclusive exclusive values, and we will take example, write some example of code and formulate or write down the formula which one uses to calculate this data, and then take a look at this formula, take it apart, and see on which part of this formula we can tune, and where we can basically extend the definition of this formula and see which generalization we get and to which complications or implications it leads. Yeah, that would be then the structure of today's talk. Before we proceed, I would like to remind you to subscribe to this channel. If you find this information useful, especially in your performance analysis and your understanding of Cube library, then give us a like. Give us a like also if you don't understand, still give us a like. And write questions or comments if you have any down below. I will later on collect them together and make a FAQ video about it. Okay, let's then go on. Here we start. Yep. Okay, so if we speak about inclusive and exclusive values in Cube, inclusive and exclusive values in Cube. There is library, there is GUI. What do we actually mean? So just a reminder, the whole performance analysis is going around the code. Code consists out of regions or basically call paths, and every region has subcalls and so on and so on. So we are talking about instrumented calls. Everything what is instrumented ends up as visible for measurement system. It gets the data attributed. Everything that is not instrumented is not visible, but it still exists. It still takes a runtime, but the measurement system of Scorpio, for example, doesn't see it. And if we talk about inclusive values, for example, over some region, we speak about the value which attributes to the whole region, including all children, subchildren, grandchildren, everything what is in there. Exclusive value, that is the value which we attribute to this region, excluding, so basically without taking into account all instrumented children, subchildren, grandchildren of this region. So basically the whole or the parts which are not instrumented. That's all, including, excluding. Let's take a look what does it actually mean, and we take a look on naive example of a code. Let's write it down. Let's see. We have main, for example. Main goes, so there is a not instrumented part of the main call, and therefore that's not visible, but it's still there. And it calls, for example, foo. Again, there is some not instrumented part, and then it calls bar, and then finalization. Okay, let's take a look at a foo. So foo, for example, there is a also not instrumented part, and it calls buts1 and buts2, for example, just to have it a little bit not trivial, like this. Then let's take a look at the call bar, oops, here, like that. It calls another call buts3, for example. So there is not instrumented part, buts3, not instrumented, that's all. And of course, let's keep it not that not trivial. Buts1, 2, and 3 will be simply trivial calls. There will be some runtime, but no subcalls. So like buts1, 2. So there is no further instrumented calls or part of the code. Therefore, for measurement system, it's not visible, and therefore it's not resolved. So it's like nothing there. But 2 is the same, like this, and but 3 is also the same. So that is example of our code. Let's identify which regions, which parts of this code we actually to which we attribute an inclusive, any values, and exclusive. So let's see. So inclusive, that is the whole region. So in all cases, inclusive value of main is this. Inclusive value of foo belongs to the whole region here, and here, and here, and here. Because this is the value, if I attribute some inclusive value for main and foo and bar, we attribute it to the whole region. Okay, so let's take a look at the main. In main we have calls foo and bar. They contribute as a part, let's say, and if the value which we use here in this context of foo, that would be the value of foo as a whole, including everything what is happening inside of foo, which is inclusive value of foo. Therefore we mark it like this. And the same is valid for buts1 and buts2, therefore it is also like that. That is their inclusive value, this here, and that's all. So there is no. So what's about all these areas which are like gaps? This is the area of region excluding their children. So this instrumented parts excluding. Therefore it is exclusive value. We attribute exclusive value to this part of the region, and that would be then, like, for example, here, that would be here in the foo, that would be in the bar, this part before buts3 and after. In buts1 and buts2 and buts3, it's obviously the same value, because there is nothing but to exclude. So there is therefore the values are here. Basically, the region to which we attribute exclusive value is the same. Okay, So let's take a most intuitive example. The code is running, therefore it is run time. So let's attribute here some numbers and see which relationship do they have to each other. So if it is runtime, so main, let's say, was go or opposite. We go from the down below. The bats1 and bats2 and bats3, they are the shortest calls, I would say. Let's see, this 1 second, 2 seconds, 3 seconds. Why not? So in a bar, there was this call bats3, which is 3 seconds, and therefore we can attribute it 3 here. And because a runtime is such a metric, so the execution of whole bar cannot be shorter than bats3 because it's metric runtime. I don't know any universe where the runtime of the whole can be shorter than the runtime of the part. Therefore, this inclusive value for bar should be bigger or equal than the for bats. Let's say it would be then 5. Right? So the same is valid for foo. So bats1 and bats2, these are correspondingly 1 and 2. And the inclusive value of all foo is then bigger than this part. Let's say it is what it would be 6, right? It's bigger. And a main is the same, foo and bar. So foo is 6 and bar is 5, which is in total 11. So therefore main should be bigger or equal than 11. Let's see, it is, what is that, 13, 14. To have simple a little bit numbers. Okay, what about this yellow parts? So excluding parts. Okay, there in the case of bats1 and bats2 and 3, it's trivial. There is nothing to exclude. Therefore, the numbers or the data is identical. So in the case of bar, the total is 5. The contribution of bats3 is 3. Therefore, the leftover should be 2 because it's a runtime metric. And of course, 2 is like total. These parts, they have to be split somehow, and let's say it is 1 and 1. And the same is in foo. So we have a total runtime 6. The runtime of bats1 and 2 is like 1 and 2, 3. So therefore, the another parts are, let's say, 1 and 1 and 1. So in total 6. And the same is with main. So total runtime 14 seconds, or minutes, or hours, or years. The foo and bar are 6 and 5, which is 11. So therefore, the leftover is 3. Let's make like 1, 0.5, 1.5. Why not? Okay, that is the, let's say, our toy example. And we have here inclusive data, which we attribute to as inclusive data to the whole, and we identified the regions which are excluding or which do not include the sub-children, sub-calls, and therefore the exclusive data, that is the yellow. Okay, how the call tree looks like, because our measurement system builds up the call tree and assigns the values in call tree. This you have seen in examples of CubeGUI and other videos. Okay, so let's take a look how the call tree would look like. Of course, we start with main. Let's take a look. Yeah. Main, and it goes to foo. So it goes to foo, and foo executes bats1. So it is bats1. Bats doesn't have any subcalls, therefore it's a leaf. And here is bats2. Right? Right? Then it gets out, and there is a bar. Where is bar? Here is bar. Bar. Okay. Bar. And bar executes bats3. So that would be our call tree, which you would get to see in the tools, in the CubeGUI, and we have also data assigned. And we see that we have inclusive and exclusive data. So that is the first basically thing to keep in mind. I mentioned it in a video about data model. I will try to link it here. If we store the data for some metric, runtime for example, we store it always in the same format. What I mean is whole data about whole call tree is either inclusive or exclusive. It is not so that data for main is stored exclusive, but foo and bar are in inclusive format. No, we don't mix it like that, not yet at least. But so the whole data is either inclusive or exclusive. So let's then assign it here and see how it behaves. So let's go first with inclusive. Okay, main is 14. Let's move it a little bit higher. Okay, 14. Foo is 6 seconds. Buts 1 and buts 2 are 1 and 2. And bar is 5. And but 3 is 3. Right? So what's about exclusive data? If we would have stored it in exclusive format, which data we would store? So exclusive. So for main, this is like 1, half and 1.5. We add it up, or actually that measurement system does it. It reports us actually only what is here 3, right? So it would be then 3. Foo is 1 plus 1 plus 1, also 3. But 1 and 2, this inclusive and inclusive value of there is identical, so therefore 1 and 2. And bar is 1 and 1, which is 2, and 3. So this is data which we would store if we would have inclusive data, so inclusive format, and this is if it would be in exclusive format. Okay, but of course, storing data in one format, that's halfway. During the performance analysis, during the work with data, we need sometimes inclusive data, sometimes exclusive data, sometimes mixing it. In CubeGUI, for example, we display it in a tree, and then if the user collapses or expands the data, we need the value of exclusive and inclusive values there and back, and therefore we need the formulas how to calculate one from another and vice versa. So therefore, let's write it down how formula looks like if we do calculations. So as first, we would like to calculate exclusive out of inclusive. So let's imagine we have exclusive, or we don't have, we want out of inclusive. Yeah? Out of inclusive. So we have basically the green data, and we would like to have the yellow. Let's go with the region main, and to obtain the exclusive value for the main, what we just did implicitly, or maybe you noticed. So exclusive for main is, so the value without children is the value of the whole minus children, without children, which is the value of whole is inclusive value of main minus what? The whole children. We have two children, foo and bar. So in this case, we put them together and subtract, right? So we put children together and we subtract it. That's all. That's the formula. Nothing else. Let's take a look at the actual data. Because we have everything in inclusive format. We have all the data which we need. We have inclusive value for the main, and we have all the inclusive value of the children. So therefore it is 14 minus and 6 plus 5, which is 14 minus 11, and it is 3. So that is how that's what we got. So let's frame it, and that would be the formula 1. If we would like to have inclusive value, let's make here separation. If we would like to have inclusive value out of exclusive data, basically. Opla. Exclusive data. What do we need to do? The same. The total part, or the value for the whole, consists out of values of parts. Which parts do we have? We have children, instrumented children, and not instrumented part. Not instrumented part is exclusive value, and the children, that's their inclusive value. Let's write it down. Okay. So we need we want to have inclusive value of main, which is it's not instrumented part, so which is its inclusive value plus what? Plus sum of the whole parts of the children, which are inclusive values. So therefore it is sum of children, but their inclusive value. Here we have a problem. We have in this formula mixture of inclusive and exclusive values, but we have only exclusive available. But we can apply this very same procedure, the same formula, to the children. So to calculate inclusive value of child, we apply the very same formula. We just go down in the call tree, and therefore, that would be inclusive value of main, exclusive value of main, plus, in this case, inclusive value of foo, which is exclusive value of foo plus inclusive value of bats1 and bats2, but inclusive value of bats1 and bats2 is identical to its exclusive value, and bats1 and bats2 do not have further children, therefore the recursion stops there. And the same is valid for bar, and therefore it is exclusive value of foo plus, and here exclusive value of bats1 plus exclusive value of bats2 plus exclusive value of bar. That would be another inclusive, so it would be of bar, which is plus exclusive value of bats3. So if we resolve all recursion down the tree till we don't have any inclusive values, we have only exclusive values, we get this formula, which is basically main plus, we can rewrite it a little bit different, all children, and here is like this, also and that is the second formula, basically, here, like this. That's all. These are two formulas, and if we have inclusive data, we can calculate exclusive format of data. If we have exclusive data, like in the case 2, we can calculate its inclusive form. Okay, let's then take a look on these formulas and see how we can generalize it, or which implications do they bring with them. But before we do that, I remind you, subscribe, give us a like, and write any question if you have any at this moment down below in the comments. Okay, good. So what do we have here? The very first thing which comes in my mind is following. We are speaking about that the whole consists out of the parts, and the whole cannot be smaller than these parts. This is actually valid only for metric, such standard metric, like time, visits, number of sent bytes, and so on and so on. That doesn't need to be generally true. The exclusive value of or inclusive value of the parent can be smaller than the total inclusive values of children or however. It depends on the definition of metric which we actually calculate. Such metric where this condition holds, I call them monotone, because the upper in a tree the values get bigger and bigger. One can resort them so that the values are always getting smaller or bigger. Therefore, I call it monotone. It's not algebraic monotone. So therefore, let's write it like metric doesn't need to be monotone aka time metric. So we have been using this fact here that the metric is monotone because we were calculating exclusive and inclusive values using this formula, and that's kind of comes natural with the fact that this we have here numbers and we have here normal plus and minus. So just keep it in mind, metric doesn't need to be. Second, we were doing here algebra using such numbers like 14, 1, 6, normal numbers. But does it have to be numbers, or does it have to be simple real numbers? I don't see why not. We can use complex numbers. So operator plus and minus is available also for complex numbers. We can use polynomials. There is also operator plus and minus. We can use maybe ratio. Plus and minus, they are not that trivial, but it is still there. We can use histogram. We can use strings. We can use formulas, and so on. As long we can write prescription for plus and minus. Then it doesn't need to be 14. It can be ABC or something else, some another object. Therefore, the data type doesn't need to be number. I'm writing like a number. It can be a general object. Of course, as soon as we say, okay, it's some object, we have to say, what does it mean, A plus B? Yeah, one needs to formulate this operator plus or minus. And again, we might have as a data numbers, but operator plus and minus doesn't need to be algebraic, this standard arithmetic plus and minus. So 1 plus 1 plus 1 can lead to 3, or can lead to 11, which would be computation. As long as one has this prescription, one can apply this formula. Okay, so operator plus and minus can be redefined. And that's basically, that's all. We have here pluses, operators, we have here data, and we have these formulas. So like, data, operator, formulas. The numbers, not numbers, operators, strange operators, and formulas, that leads to this property of monotone. Okay, so about operators and about data types, I would like to say a little bit more. Um, if we reformulate or redefine operator plus and minus, there are conditions which one has to keep in mind. First of all, the operator minus here, we speak about subtraction of something, so excluding. So the operator minus here plays a role of inverse, which means data plus operator plus and minus, they are building the group, and there is a common zero and there is inverse operator. So as long one can do that, one is fine. If one cannot do that, usually one can formulate only one operator. One cannot formulate this inverse. Then one cannot apply formula 1, but one can apply formula 2. There is only one plus operator. That puts a condition to the data and this operator and type of data. So if we can formulate only operator plus or only one operator, then we can use only formula 2, and therefore the data which we store has an exclusive property or format. If we can formulate both operators, then we can store data in inclusive format, because then we can apply plus and minus. If the operator minus is not an inverse of plus, but something completely weird, like for example, if we define operator plus as a maximum and minus as a really minus, so how it would look like then? Let's take a look at this example. So in this case it would be then 14 minus, but operator plus is our maximum, so it is then maximum of, and what do we have here? 6 and 5. Maximum of 6 and 5, which is 14 maximum minus 6, which is 8. 8 seconds. So what this 8 means? This is the part of the main without maximal region with maximal execution. It has another regions, another children, but not the maximal one. On the first look, it's completely weird metric. Maybe in some performance analysis, in some analysis, it makes sense to have such metric. Therefore, one should keep in mind that plus and minus, how do they behave? What does it actually mean? So technically, the Cube library will calculate such a value and display for you, but it's up to user then to try to understand what this 8 means. Yeah? Okay. Then another things which one has to keep in mind. We have here formula, and I wrote it down in such simplified form. So first inclusive value, then minus, then the sum, and so on and so on. There is implications connected to this. First, let's speak about operator plus, for example. It's valid also for minus. The operator has to have a commutation property. It has to be a plus b is the same like b plus 1. Why? In different parts of Cube library, we perform summation in different order. Sometimes it is from links nach rechts, sometimes from rechts nach links, sometimes completely shuffled, sometimes it is asynchronous, and is adding up, and result should be the same. Should be. So if the operator plus which one define has this property, it will be the same. If it doesn't have this property, Cube library will calculate the sum happily and present your result. This result will be different every time depending on how this actually summation happened, and the user will have a really hard time to understand why this value is so, another value is another, simply because the commutation does not hold. Example of such not commutating operator plus, I can, that is like angle summation on a sphere, for example. That's not commutating operation. So if we go in one direction, we end up in one place of the globe. If we go in another direction, we go in another place in the globe. Therefore, one should not keep it in mind. And another property is, of course, A plus B association property. Like this should be the same like A plus B plus C. Sometimes we sum one part of the formula, then another, then put it together, and the result should be the same. If this property does not hold, again, result of the calculation will be different depending on the algorithm, and the user will have hard time to understand why in one part of the execution is one value and another value. I cannot now give an example of such an operator, but one should keep it in mind, especially if one redefines operator using the derived matrix engine. Okay, and another one is, of course, as I already mentioned, plus and minus. If they are building the group, they have to have common zero. If they are not building common zero, they are not building the minus is not inverse then, and then again the formula will be calculated, but the result will be completely weird, and user will have a really hard time to understand what's going on in there. Okay, that is one thing. Another thing what I wanted to point here, so that is this. If we take a look at the Formula 1 and 2, so in the Formula 1, we already on the first level, we stopped our resolution of formula. So we took the value of our main and took direct children, and the data was there, and we are fine. In the case of Formula 2, so basically calculating inclusive value out of exclusive, we had to go all the way down in a tree. And we see that to calculate the inclusive value of main, we had to gather basically hold the data. So this this one should keep in mind if one chooses to store data in exclusive format in inclusive format, because that has impact on performance of calculation within the Cube library. So here in the second case, we have to sum up the whole data. In the first case, only parts. And decision in which format we store the data then leads to different performance of this operation. And B, usually the data in exclusive format is way more sparse than the data in inclusive format. And from one side we need less data to calculate, but we have it more in storage. In exclusive we have only few data stored, but we have to calculate a lot of data, basically a lot of zeros. So this is I wanted to point out. Here I also point out that, for example, in the case of the Formula 2, we to calculate inclusive value of the region main, we have to sum up of the data of all its children. And in the case of the first formula number 1, only direct children. Depending how do we enumerate this data, how do we store it in a data file, it's better to enumerate it differently in order to preserve locality. This I will explain later on in a video about data layout. I don't go here further. Simply the fact that we have inclusive and exclusive format leads to different layout in a data file. That's one thing. And the last thing what I wanted to mention, Cube library has derived metric engine. I will speak about it in another video, just a little bit ahead. Derived metrics, or Cube has two types of derived metrics, pre-derived and post-derived. Why they are pre and post, I will explain it in our own video. The fact is, if cube or if one formulates pre-derived metrics, the data is being calculated using these formulas basically. Yeah. So there is still such relationship between inclusive and exclusive value via this formula. So they are related. The result might be very, very not obvious because operator can be redefined and data can be redefined. Results can be very interesting, but there is related via arithmetical formula. If we have post-derived metric, the value for inclusive inclusive value for some region might be completely unrelated to the value for its exclusive value, because for the post-derived metric we actually formulate the expression or formula how do we calculate inclusive and how do we calculate exclusive. Of course they are related in sense of one formulates the data, but technically they might have completely different expression, and the only thing what connects them is the interpretation of the user. So the one expression is inclusive value, is attributed to the whole, and another expression is exclusive value, is attributed to the whole, except, maybe not except, the children. So there are basically two values. And that is special by post-derived metrics, and this one should keep it in mind. To summarize, yeah, just shortly, the metrics in cube do not need to be monotone. They are most of them are monotone, so basically value of parent is bigger than the sum of value of the children, but they are not necessary like that. For example, average execution time cannot be metric, how we call it, which is nothing else than ratio of inclusive runtime over exclusive number of visits. This metric is not monotone. Value for inclusive and exclusive value of the parent might be completely bigger, smaller, unrelated to the values for the children. Data type. So basically data which we store in the metric doesn't need to be number. It can be, or normal number. It can be a complex number, it can be ratio, it can be formula, it can be object, statistic, whatsoever. As I already explained in a video about data type, data model, this data type should be like some common, equal to the whole metric. So we cannot have part of the data numbers and another part of the data statistic within one metric. It would be two different metrics. Okay, and operator plus and minus, that's very interesting thing, can be also redefined. If the data type is not trivial, then operator is also not trivial, so one has to keep it in mind. If the data type is still number, like by derived metrics, operator plus and minus can be redefined. And depending which properties do they have, these operators plus and minus, are they related via inverse or not? Are they not related? Do they commute? Association property, if that's hold or not, it leads to different results, and that one should keep in mind. The cube library will allows everything of it. It will perform calculation. Interpretation of the data is up to the user. If the user defines crazy stuff and gets the craziest things. Okay, and the last things, our derived metrics, especially post-derived metrics, goes away from these formulas. It simply defines one value for exclusive, one value for inclusive value. They are separate, and one should keep in mind which is what and what does it mean. And in CubeGUI, if we expand the tree, we show exclusive value. If we collapse, it's inclusive value. That's all. Which value, which data will be displayed depends on all these things which I just mentioned. It depends on the data type, it depends on the operators, it depends on the kind of a metric. That's all. I think that's all what I wanted to say in this video. I hope you understood that inclusive and exclusive data, or this understanding of these formats in the Cube library is a little bit general, more general than one would think. And this one should keep in mind when one takes a look at the data in the CubeGUI. I hope you found this small lecture useful, and it will help you later on in your performance analysis. Please subscribe. If it helps or not, give us a like. And if you have any questions, put them down in comment, and I will answer them later. And see you next time.